This lesson's on solving rational inequalities. So now we've got a rational function that instead of being equal to a certain value is either greater or less than a certain value. Now, we have dealt with polynomials inequalities already. Our strategy is simple: take the polynomial and graph it. Then we could visually see when the graph was greater than or less than a certain value. Will the same strategy work here? Absolutely. Except there's one little trick I got to show you later. Okay? Most of these steps you've already seen, so I've already got them all typed in and filled in here for you. This question says solve 2x squared minus 3x minus 5 over x squared minus 3x minus 18. And then we want to know when that is greater than 0. Well, instead of trying to find when it's greater than 0, all I'm going to do is graph it. And then once I have the graph, I'll be able to see visually where it's greater than 0. I'll also build a chart in the meantime, which I think is a slightly more powerful way to get the answers here. I won't say it's better. Graphing has huge advantages as well, but the chart has some big power advantages here. So first go through the steps to graph f at x equals 2x squared minus 3x minus 5 over x squared minus 3x minus 18. Let me just highlight these steps here for you. For x-intercepts, set y to 0. So I set the y to 0 here. That resulted in going numerator equals 0. In this case, I factored it and found my two zeros, 5/2 and -1. Those two x-intercepts are invaluable when I'm going to make the graph or to go make a chart. Over here, I found the y-intercepts by setting the x value to 0. I just subbed in 0 into the function and got 5 over 18. Actually, as it turns out, that's a good step for graphing. It's actually not needed to get the answers in this particular question. And I'll show you why later, but just to show all the steps for graphing, I put it in here. For domain for domain issues, vertical asymptotes, we set the denominator equal to 0. The denominator is up here, x squared minus 3x minus 18. Again, these were the restrictions that we used to call them restrictions in grade 11. And so I factored here. You might have to use the quadratic formula on one of these questions when you get down to a quadratic like this, but this one happens to factor, and I get 2 vertical asymptotes. Now, another piece of information is the horizontal asymptote. And the horizontal asymptote, in this particular case, because the degrees are equal, and I'll use a green here, because the degree of the numerator and the denominator are equal, then I go ratio of the coefficients, which is 2 over 1 here. And so it would have a horizontal asymptote of 2. Also needed to graph, but not needed to build the positive interval chart. Here's the positive negative interval chart. What I did is I took the original function, 2x squared minus 3x minus 5 over x squared minus 3x minus 18, and I put it in factored form. And then I listed all the factors down the side here. You don't have to do that, but just for the sake of seeing all the steps here, I did that in this one so you can see where I got the answers from. You could just do the final step here and figure out whether it's positive or negative from there. And by that, what I mean is you just choose a representative for each of these sections. We've done this before. And I chose -5 here. That's less than -3. Something that's less than -3. And I just look at what happens here. So 2 times -5 minus 5 is negative. -5 plus 1 is negative. -5 plus 3 is negative. -5 minus 6 is negative. And when I multiply negative, 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 all 4 negatives together, I get a positive answer right there. And I went through that for each part of the chart. We've shown that chart before. Well, actually, you can see right here, I said the graph. I've got the graph coming up here, but you don't need the graph to answer the question. The question was, when will this function right here, f at x, be greater than 0? And it's greater than 0 right there, and right there, because that's where it's positive. See, that's what it asked for. Where is it greater than 0? So my answers are right here. X less than -3, -1 less than x less than 2.5, and x greater than 6. So the chart gives those answers directly in a very, very efficient manner. So I'm a big fan of the chart. However, if you wanted to graph it, this shows the graph, everything here. And so if you wanted to find those intervals of when it's greater than 0, it's greater than 0 in here. It's greater than 0 in here. And it's greater than 0 over here. And those are the same intervals we found above x less than -3, between -1 and -2.5, and greater than 6. Okay, so if you can graph rationals, you can easily find the intervals where it's greater than 0 or less than 0. If you can't graph rationals, well, you should go back and work on that, because you're seeing this is starting to pile up now. If you can't graph rationals, you can't do this section here, so that's a big problem. So that work needs to be, it's the focus of everything. The good news is if you can graph rationals, you should be able to come back here and go, oh, so I just graph it and look at it when it's greater than 0. That's all I have to do today. And the answer to that is yes, except for one little thing that I have to show you. What I'm going to do to show you that one little thing, which is really the big deal of this lesson. See, this lesson, if you could graph rationals doing inequalities, you just sort of say, okay, where is it greater than 0? We could have asked that question as soon as you were done graphing rationals. But there's a little something more that comes up in some of the examples. One of your homework questions here, I'm going to steal one of your homework questions, number 4D. And number 4D asks you to go find out when 7 over x minus 3 is greater than or equal to 2 over x plus 4. And that's a major league problem. That's very different than the question I just worked on, because the question I just worked on was asking when is it greater than 0. That's a very simple version of the question when it asks you for greater than 0. Oh, it's simple. Sorry, simple's an exaggeration. It's a much simpler version. This one doesn't have it equal to 0. Now, then you ask yourself, can I use the rational equation method and just multiply through and get rid of the fractions? And the answer is a big no. And I got to put that in big letters here. Can't multiply by the common denominator in inequalities. And the reason you can't do that is that you don't know when you're multiplying by a negative. And if you don't know when you're multiplying by a negative, you won't know when to reverse the inequality. I don't know if you remember that now from solving inequalities, is that when we multiplied or divided by a negative, we had to reverse that inequality. And if we don't know what we're multiplying by, if we don't know whether it's positive or negative, we won't know whether to reverse the inequality, and we can get exact wrong answers. So the short version of that is the method we used on rational equations of multiplying through by the common denominator will not work here. What you've got to do is actually get this thing equal to 0 on one side by bringing that term over. Now it's a 0 over there, which is very exciting, because then if I can just graph this thing, I'm home free. But the problem is that this thing isn't a rational function at this point. It's two rational subtractors from each other, which is very difficult. And in fact, one of the homework questions asks you to do a question like this by just looking at the graph. And all they're asking you to do is look at the graph and see where one is greater than the other. So I guess I could do that. I could graph this one and graph this one. Then, after very carefully graphing them, check to see when one is greater than the other one. That's going to be a load of work compared to what this is. So, to get these two things together, I need a common denominator. The common denominator will be x minus 3 and x plus 4 multiplied together. So what I'm going to do is multiply this rational by x plus 4 on the top and x plus 4 on the bottom. And I'm going to multiply this rational by x minus 3 on the top and x minus 3 on the bottom. You actually did questions like this, where you had to find a common denominator between these in one section in grade 11. It came up once in grade 11, so it might easily have left your memory. But so far, all I've done is found a common denominator. And once you have a common denominator, I can put together the numerators over the common denominator. That's what we always do when we're adding and subtracting fractions. We add or subtract the numerator, but we keep the denominator the same. I got a little multiplying out here to do. And so when I simplify that all down, I get 5x plus 34 over x minus 3, x plus 4. I think you'll find it easier to factor whenever you can, and it's a weird factor here. And I'm going to use a decimal. But when that's in nicely factored form, I think you'll find things a little bit easier to work with once that's all factored. Now, just to be clear, up here, I went through all the procedure to graph. And if you want to do these questions by graphing, then you should go through all those steps. I'm going to show you a shortened version, which gets me right down to the chart. The only things I need for the chart are x-intercepts. And so I want to know when 5 times 5 bracket x plus 6.8. I want to know when's that equal to 0, and I get x equals negative 6.8. So I've got the x-intercept that I need for my chart, and I need the vertical asymptotes. So to build that chart, not for graphing, but to build that chart only, all I really need is the x-intercepts and the vertical asymptotes. And what I mean by that is, those are the only times this thing switches from positive to negative. Look up here on the chart is what was used all the way across here, and I'll just highlight it here. To build that chart was x-intercepts and vertical asymptotes. Those are the only times it can change from positive to negative, so it's the only thing that needs to be on the positive-negative chart. So, I need a little more space here. That's going to take a second. Just hold on. There, that got me another page. So here's my chart. Start with the lowest of those x-intercepts and vertical asymptotes, negative 6.8. Then I want to know between that x-intercept and this one, and then between negative 4 and 3, and then greater than 3. So I've used all those x-intercepts and those vertical asymptotes. Now I'm also going to show you a shortened way of doing the chart here. So this thing I want to find out about, when I factored it, I got 5 over x plus 6.8 in the numerator. The denominator was x minus 3, x plus 4. I just got those from right up here. It's all right there. Okay. So now you choose a representative in each of these sections. For instance, in this section, I'm going to choose negative 10. And negative 10 on the top, 5 will be positive. Negative 10 plus 6.8, that'll be negative. The denominator will have negative 10 minus 3, which is negative. Negative 10 plus 4, which is negative. And you put all those things together, this section will be negative. You see how I use the little small positives and negatives to do my thinking, but then I draw a giant negative there to let myself know what happened in this section. Then a representative number between negative 6.8 and negative 4 is negative 5. And negative 5, let's see, 5 will be positive. Negative 5 plus 6.8, that'll be positive. Negative 5 minus 3 is negative, and negative 5 plus 4 is negative. When I multiply all that stuff together, I'll get a positive. Positive, positive is positive. Negative times negative is positive. I'm going to do one a little bit faster so that if you're still not convinced on the value of the chart, you can see how fast it can go once you get good at it, once you practice these a few times. My representative in here is 0, so I get positive, positive, negative, positive, negative. Maybe you think I cheated by using the section with 0 in there to do my fast one, but it's fast every time once you get good at it. I'm going to use 10 in here. That's a number that's greater than 3. Positive, 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 positive. That whole thing comes out to be positive, and I'm ready to answer my question. I wanted to know when that function was greater than or equal to 0. So that's this section, and this section is when it's greater than or equal to 0. So I need negative 6.8 less than or equal to x, less than or equal to negative 4, and I need x greater than or equal to 3. Now watch out in these questions, folks, because you'll look in the back of the book and you'll miss that the answer in the back of the book doesn't say something like that. It doesn't have less than or equal to right here. It just says less than, and that's very confusing. Why can't it equal negative 4? Way up here, right here at the start. Here's the restrictions. Remember I said it almost never comes up? Well, here it does come up. X can't equal 3. X can't equal negative 4. And when I go down here, in my answer, I'm saying, oh, x less than or equal to negative 4, and it can't be equal to negative 4. So I have to get rid of that right there. There's my complete answer there. Okay, so a couple little quirks there, and that is question number 4D in your homework, I believe. And so when you get to that one, I would still try it. I would still try and repeat it, but you got a nice full solution here. And watch out for that common denominator stuff. Watch that over again, and if you have to, on getting common denominator to get one rational on one side and greater than or equal to on the other. Greater than or equal to 0 on the other.